lecture tonight. I'll try to be quick. All right, Shreyas, can you see my screen?
Yep, I can see it. Okay, yeah.
All right, great. So tonight we're talking about something very exciting. We're talking about neural networks, and this is a lot of what we've done so far have been kind of basic algorithms. This is getting slightly more complicated, but I think it's something that everyone here can understand, at least at a high level. And this is something that I actually happen to use every single day at my job. That is neural networks. So today's learning objectives are going to be, what is a neural network? We'd like to identify and define parts of a neural network. So some terms we're going to see are activation functions, nodes, layers, outputs. And we're going to talk about how you might go about designing a neural network when you've got a problem in mind. So first I want to give a little bit of background. Surprisingly, the concept of neural networks has actually been around since the 1940s. In 1940, or sometime around then, Alan Turing asked a question to the scientific community whether or not it was possible for machinery to show intelligent behavior. So mathematicians pondered this question and began to try to replicate human intelligence by creating computational models of the brain. And they based these on their understanding of human thought patterns at the time. So in 1943, Warren McCulloch and Walter Pitts published this first concept of a simplified brain cell, the McCulloch-Pitts neuron. And that's basically where this field kind of got started. About 15 years later, Frank Rosenblatt extended their research and created the first concept of what we call the perceptron, which really led the way to what we consider modern neural networks. So here's kind of what they thought about a neuron. So I'm not a biologist. Some of you might know more about this than I am. But essentially, the neuron accepts electrical impulses in this input. Those inputs are shown on the left side. And those electrical impulses are transmitted through the neuron. And under certain circumstances, the neuron might fire an electrical output. It's hard to tell what those conditions might be, but that's essentially what they tried to replicate using a neural network. Inputs coming in on one side, and if the signal was strong enough, they figured it should provide an output. And that's how they got started with a classification example. So they built a single artificial neuron for binary classification. So remember, when we're talking about classification, specifically binary classification, we're trying to assign an input to a pair of classes. And in this case, we'll call it a positive class or a negative class. Don't assign any meaning beyond that. Positive doesn't mean good and negative doesn't mean bad. It's just two ways to denote the two classes. And so let's let X be an n-dimensional output or input, sorry. So X equals X1 through Xn. And we've done stuff like this before. We've seen this in linear regression and logistic regression. So we'll then define the variable Z, which is a linear combination of those variables. Essentially, this looks a lot like the linear regression model. We have some bias term. Let me see if I can, can't draw right now. Keep skipping. That's okay. So we've got a bias term or an intercept term, and then we've got theta 1 times the first input, theta 2 times the second input, theta 3 times the third input, and so on. And then we define what they called a decision function. So that's phi of z. And they define that as follows. Phi of z equals 1 if z is greater than or equal to 0, and phi of z is -1 otherwise. So we compute z based on our current estimate for our parameters using x, and if it's positive, we assign 1. If it's negative, we assign -1. And so the idea is to find parameters so that x is mapped to the appropriate class, 1 or -1. So this is a lot like what we saw with logistic regression, just with a slightly different decision function here. So we translate this model on the left, this image that we saw a couple slides back, to this mathematical concept of an artificial neuron. So on the left side, we have all of our input variables. So we have x1, x2, x3, x4, and xn. And for convenience, we're just going to add a 1. That is our intercept term. So if you look at this screen, you can imagine when we define z, that z equals theta 0 times 1, and then theta 1 times x1, and so on. So essentially, this image tells us how to compute z. So we take 1 times theta 0, theta 1 times x1, theta 2 times x2, theta 3 times x3, and so on to give us z. And then once we have z, we can go ahead and compute phi of z. So the concept of a single neuron is actually not that complicated, really. But of course, it gets slightly more complicated when we want to generalize this to make it more useful. So we start by defining a neuron, again, to predict whether an input x belongs to a positive or negative class. And instead of defining that simple function phi of z, which only operated on whether or not z was positive, we'll let phi of z be any differentiable nonlinear function. And we're going to call phi of z as an activation. We'll call it an activation function. So many of you have not had calculus, so this term differentiable might not really make sense. But essentially, you can think of it as any continuous smooth function. So it doesn't have any weird behavior, no sharp turns in it. It's a smooth function. And so again, we try to find parameters, again, theta equals theta 0 through theta n, so that x is mapped to the appropriate output. And depending on the choice of activation functions, this neuron could actually be used for regression or classification, as we'll see in a little bit. And just as an advanced concept, it is possible that the activation function doesn't have to be differentiable everywhere, and there are some that are actually very common that are not differentiable, but that's a little bit beyond the scope of tonight's lecture. All right, so now we're going to actually see a neural network. Before, I'm going to go back a couple slides real quick. We had x1 through xn contributing to a single neuron in the second, what we'll call layer. Here, we're going to have 1 through xn contributing to many different nodes. So imagine we just replicate that behavior that we saw a couple slides back. Here we've done that k times. So 1, x1, x2, x3, x4 through xn all compute a new neuron, h1, and they all compute a new neuron, h2, all the way through h sub k. And then all those, that second layer of neurons contribute to a new variable that's going to be our output, and we'll call that y hat. So again, just to reiterate, from our inputs x1 through xn, we could compute outputs of k independent intermediate neurons. Those are going to be h1 through hk. And then we'll use those k neurons to compute the value of an output neuron, y hat. So basically, we've just replicated that behavior we saw a couple slides back and stacked a couple of these neurons together and created a multi-layer neural network. So as we've as I've mentioned, we'll actually call this a dense multi-layer neural network. And we call it dense because every node in a layer is connected to every node in the next layer. So x1 through xn all connect to each one of these h's in the first layer. Each node in the first layer connects to every node in the second layer. And we can have as many layers here as we really want, assuming our computer can handle it. So up until layer M, in which we have P nodes, and then those layers, those nodes all connect to the output layer. So I've given us a little key here on the side because right now we're starting to see a lot of indexes or indices. So in the input layer, we just have simply x1, x2, x3, and so on. That's kind of easy to keep track of. But in layer 1, we see h11, h21, h31, hk1, and we see h12, h22. Essentially, when we look at this hij, where this j is the superscript in parentheses, I represents the index of the node within the layer, and j represents the index of the layer. So if I'm looking at layer 2, and let's say I look at h32, h32 is the third node in the second layer. And each line on this neural network represents an independent weight, or another term we've used is independent parameter. So every arrow in this represents a different parameter. So as you can see, we're starting to look at models that have many more parameters than we initially investigated. All right, so as I said before, each one of these arrows is its own parameter. And in order to keep track of this, we need a mechanism for kind of naming each one of these arrows. And it starts to get a little bit complicated, but there's a good way to do it. A lot of resources will use different notations, but we'll try to stick with one of the more common ones. And so I'm looking at this heavily weighted purple arrow here that connects the nodes h31 to h22. So that's the third node in the first layer connected to the second node in the second layer. And we'll call that parameter theta 322. So why do we call it theta 322? It's actually kind of easy. So the parameter, this 2 that's in parentheses as a superscript, contributes to a node in the second layer. And this 3 here represents that the weight is for the multiplier from the third node in the previous layer. So again, this connects from h31 to h22. So the 3 comes from this node in the first layer. And then this final 2 here as a subscript, this is because we connect h31 to the second node in the second layer. And again, as a reminder, this first layer with the x's is actually called the input layer, and the ones with h11, h21, and so on, that we'll call the first layer or first hidden layer, because in general, we don't really see these layers when we're looking at it in terms of a model. So next, the question becomes, how do we compute the value of each node? Well, each node is computed by taking the sum of each of the nodes from the previous layers multiplied by their corresponding weights connecting them to the that connect the two nodes. And once we've computed that, we apply the activation function. So this looks a little bit complicated, but we can break it down into a few steps. So the first step is to compute z sub I, and that's essentially this linear combination that we saw way back here in slide 7. So again, z equals theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 and so on. But now instead of the x's, it might just be nodes from a previous layer, not the actual inputs. And then we multiply, again, all of the weights, the theta g sub I, theta g I j times hg j minus 1. So this hg j minus 1 is a node from the previous layer. The theta is the weight that connects it to the node in the next layer, hij. And then once we've computed this sum, we apply the activation function. All right, so this might sound pretty complicated, but it's actually not too bad. We'll go through a quick example here of how we might do this in practice. So I've computed, or I've created a very simple neural network here. So we have our input layer, which is 1, x1, x2, x3. We have one hidden layer, that's 1, h1, h2. And then we have an output layer. And we'll use that original activation function that we saw in one of the first few slides. And let's compute y hat based on the input x, which is x1 equals 2, x2 equals 1, and x3 equals 4. And I've drawn all the weights in the diagram. So the weight connecting the node x1 to h1 is 2, and the weight connecting x1 to h2 is -4. So we'll go through this computation. First, we'll compute z11, and remember z11 is the value of h11 before we apply the activation function. And so how do we compute that? Well, we have 3 times 1, and then we have 2 times x1, but x1 is 2, so that's 2 times 2. And then we have 0 times x2. X2 is 1, so that's just 0 times 1. And then we have 7 times x3. X3 is 4. So when we sum that all up, we get 3 plus 4 plus 0 plus 28, and that gives us 35 for the value of z1. If this isn't making sense, that's okay. It's just important to understand that there's inputs that get mapped to outputs via a collection of nodes that belong to layers. And it might be helpful after this lecture's over to go back and watch the video again and try to compute these for yourself. Now let's look at Z2. Z21, again, that's the value of H2 before we apply the activation function. So we have, for H2, we have 1 times 1. We have -4 times x1, and x1 is 2. We have -2 times x2, x2 is 1. And we have 1 times x3, and x3 is 4. So we have 1 minus 8 minus 2 plus 4, which equals -5. So now that we have Z1 and Z2 for the first layer, we can go ahead and apply the activation function. So H1 is just this function, phi of Z11. So that's just phi of 35. And recall that phi returns the number 1 when its input is positive. So since 35 is positive, it will just return the number 1. H2 is equal to phi of Z21, which is equal to phi of -5. And again, since phi has a negative input, it outputs -1. All right, so we've done all of the computation necessary for getting the values of the first hidden layer. And then we can compute Z12. So that's just going to be the value of y hat before we apply the activation function. And we have 2 times 1 plus 10 times h1. And from the previous computation, we said that h1 was 1. We have 4 times h2. And from the previous computation, we said that h2 is -1. So this ends up being 2 plus 10 minus 4, which equals 8. So when we apply phi to z12 to get y hat, we see that phi of z12 is phi of 8, which is equal to 1 since its input is positive. So given the input 2, 1, 4, we've passed all that information through the neural network. We first computed Z1 and Z11 and Z12. Sorry, Z21. It's kind of gets confusing, so we have to be careful. So we computed Z11 and Z21. Then we applied the activation functions and we computed H1 and H2. And given H1 and H2, we computed Z12. And then we applied the activation function to give us Y hat. All right. So again, I don't expect that everyone that's following along understands exactly how to do this. It might take a couple times watching this video or a little bit of extra reading because this is one of the most complicated models that we're going to talk about. But you can see that we can pass an input through a series of intermediate layers and nodes, and then use those to compute following layers and nodes, and eventually compute our output. So you can see that this is very, very flexible. So you might ask, how do I design a neural network? You probably have a lot of questions about that. How many layers should there be? How many nodes should be in each layer? Does each layer need to have the same number of nodes? What should the output layer look like? And what activation function should I choose? And furthermore, we keep talking about cost functions, but I haven't mentioned that at all so far today. So what should our cost function be? Some of these questions have definitive answers, and for others, I'll just try to provide some general guidance, and others you basically just have to learn to tune based on your experience. So let's start with one that, for the most part, has a definitive answer. What should the output layer look like? So if you're trying to solve a regression problem, that means to predict a real number output, you'll probably just have a single output node. So you'll have some number of inputs. Think back to when we were trying to predict test scores. We had the number of hours studied and the homework score. Those would be 2 inputs, and then they get passed through the neural network, and we just have a single output, and that's the test score. If we're trying to solve a classification problem, again, we're trying to predict a label or a class associated with the input, we need to consider the number of classes before we can answer this question. So for a binary classification problem, we can do this with a single output node, kind of like we just saw in the previous example, where it's either 1 or 0 or 1 or -1. Either way, it might represent the probability that an observation belongs to a positive class, or it might just represent the class that it gets mapped to. There's a couple different ways to do it, both of which are perfectly acceptable. However, for a multi-class classification problem, you actually want one output node for each class. And generally, each output value will represent the probability that the observation belongs to that respective class. So for example, when, not to steal Shreyas's thunder, but he's going to show an example where we try to map handwritten numbers 0, 1, 2, 3, 4, up through 9. We try to determine what number a person attempted to write by hand. And in that case, we'll need to have 10 output values, 1 for each class. So does each layer need to have the same number of nodes? The answer to this is no. And there's actually many types of neural networks that are designed for very specific purposes, which specifically utilize different sizes for each layer. So a couple of examples that we're not going to talk about tonight, but you may have heard about or read about. One is called variational autoencoders, or VAEs, or convolutional neural networks. they often use a series of very different types of layers. So in general, the answer is no. But if you want to have the same number of nodes on each layer, that's okay too. It's kind of just dependent on your problem. And again, one of the things you'll learn to adjust over time as you get more comfortable using neural networks. So how many nodes should there be and how many layers? So this is actually a question that is more suited for the next lecture, lecture 7, when we talk about overfitting and underfitting. But here's a basic definition. When a model does not have enough flexibility or enough parameters to learn the patterns and relationships present in the data, we'll call that underfitting. And when the model has too many parameters and tends to memorize the training data, but doesn't perform well when it's exposed to testing data, we call that overfitting. So if we see that our model is overfitting, we should try to remove layers or use fewer nodes in each layer. And if your model is underfitting, you may want to add layers or use more nodes per layer. And some applications actually have special types of layers that you can use. So there's a thing called convolutional layers, which are used with images, and those look for certain features that might appear within an image. If you don't fully grasp what's on this slide, that's okay. Shreyas and Shraman will be talking about this in much more detail on Tuesday evening. And then you might ask, what activation function should I use? Well, it turns out there's tons of activation functions. You can probably go and look up on Wikipedia, you can probably find 30 or more different activation functions. I've found this image that highlights a few of the most common ones. So we've seen sigmoid in the past. We use that for logistic regression, and you can actually use that same function for neural networks. You can use something called the hyperbolic tangent, which actually looks a lot like the sigmoid function. You can use the ReLU, which stands for rectified linear unit. And essentially, the ReLU is just the function y equals x when x is greater than or equal to 0. But it's equal to 0 when x is less than 0. And then there's a function called the leaky ReLU, which is very similar to the ReLU, but behaves a little bit differently when the input is negative. And something called the max out, which I won't discuss in too much detail here. And also my screen disappear. Shreyas, can you see my screen still?
Yeah,
right.
I can see it.
Yep, sorry about that. And then finally, the ELU, or exponential linear unit, which again is kind of just an advanced fancy version of the ReLU. So for some classification problems, you may want something called a softmax function. I haven't discussed that here because it's a little more complicated and can't really be demonstrated graphically very well, but it's a pretty simple concept that you can go read about if you're interested. And when I'm designing neural networks, I personally like sigmoid functions, ELUs, and leaky ReLUs, but that's kind of a personal preference, and you might find success using other ones based on the applications you're interested in. So as we've talked about, there are a lot of different choices when designing a neural network. The number of layers, the types of layers, or the number of nodes, the type of activation functions, and there are a lot of special architectures that we've maybe mentioned, but we haven't really discussed tonight. Convolutional neural networks, recurrent neural networks, long short-term memory networks, variational autoencoders. So when in doubt, don't try to build your own neural network from scratch. Try to find an example of a similar problem that someone has already solved and see how an experienced machine learning practitioner has solved the problem. And finally, we need to talk about what the cost function should be. This is dictated by the problem rather than personal preference in most cases. So if you're using the neural network for regression, we can use the mean squared error cost function, just like we saw in our second or third lecture, which was on linear regression. If you're using the neural network for classification, we can actually use the same cost function we saw in logistic regression if it's a binary classification problem. And this function actually has a special name. It's called the binary cross entropy. I won't go into why it's called that, but again, it's one thing that you're more than welcome to go look up. If you're using the neural network for multi-class classification, there's actually an extension of the binary cross entropy called the categorical cross entropy. And most of the time, people don't build neural networks from scratch. They use a package such as TensorFlow or Keras, if you're using Python, that build the neural networks for you with a little bit of input by the user. And these cost functions will often be referred to as loss functions or losses. So if you see loss function or losses, that generally is just referring to the cost function associated with the neural network. And with that, I'm going to pass it over to Shreyas, who's going to give us a pretty cool demo on using neural networks for a image classification problem.
Thank you, Dr. Willard. That was actually a great lecture. So now let's actually get started on our problem, okay? So our problem today is going to be actually classifying handwritten digits. So before I actually get started, let me share my screen. All right, guys, can everyone see my screen? Dr. Willard, can you see my screen?
Yes, I can see it.
All right, nice. Okay, so essentially, as I said before, the problem we're trying to solve is the problem of classifying handwritten digits. So what I mean by that is, let's say that you were given one of these zeros, as you can see here. So all of these are zeros, as you can see. And as a human, you can pretty obviously tell that all of these are zeros without much thought. But how can you have a computer just say all of these are zeros, all of these are ones, all of these are twos, so on and so forth. So that's sort of our goal. And the way we'll do that is using a neural network. Okay. So with that being said, let's actually get started on this. Okay. So as Dr. Willard said, we usually don't build neural networks from scratch. Instead, we use already inbuilt packages or inbuilt libraries. And in general, for many machine learning problems, we use of those inbuilt libraries. And in the case of regression, if you recall, we used the scikit-learn library. But in this case, we'll be using the Keras library, as you can see here. All right. So first, we're going to import Keras. And then we'll first import Keras. And then we'll import these four imports as well. So let's talk about what each of these mean. So now I'll be importing something called a sequential model. And the sequential model is essentially just a model which has a bunch of layers. So you can think of it as sort of initializing the neural net. All right. So next you have from Keras.layers, let's import the dense. And that's just going to be used to sort of just add a bunch of more dense layers. Okay. So this is now we'll be importing the two categorical, and essentially what that is this. I'll show what that means in just a second. But essentially what that is it's to instead of having one output node, we want to have 10 output nodes, and that's why we use two categorical. And that might seem pretty abstract right now, but I'll talk about what that means exactly in just 5 minutes or so. And lastly, we're going to import matplotlib. And matplotlib is just another sort of, it's just used to this graph, and I'll be using it to actually show each of the test images and training images. All right, so let's run this. So next next thing will be actually to load the minced data set, and essentially the minced data set is a data set which is which is just a collection of handwritten digits and what the actual digit is. So essentially on our X, you'll have each of these digits, as you can see here. And then on our Y, we'll have we'll have the actual digit name, okay? So that's the MINT data set. And this is already it's already a data set that CARES already has. So we don't have to actually just import it from somewhere else. We can import it straight from CARES. So now let's do this. So now we'll actually split our data set into training and testing data sets, okay? So we'll have X train, Y train, X test, Y test. So now before we actually build a neural net, let's actually understand and visualize the data, okay? So, so let's do that. So first let's actually see the shape of everything. So first let's have X train.shape. So essentially what this means is that we have 60,000 images and each image is 28 by 28 pixels long, right? So we have 60,000 images, 28 by 28 pixels long. Now we have, let's go to X test here. So let's do X test.shape. And here you see that we have 10,000 images and each of these images are again 28 by 28 long, all right? So that's sort of just our data. And now let's actually look at our data examples in particular. So first we'll use this PLT. So we're going to use matplotlib to actually do that. So we'll do plt.imshow to actually sort of show us our data. So if you do xtrain, 0, let me comment this out for now. So if you do xtrain, 0, we run it, we'll see that we have a 5. Okay, so the first image is 5. Next we do xtrain 1, we'll get 0. And we'll use the imshow function as I said here to actually do this. And the cmap equals plt.cm.binary. This just ensures that the image is a black and white image. So this image, as you can see here, this is actually a grayscale image. So what that means is that we have, as you can see, we have 28 by 28 image with a bunch of pixels in it. And then each pixel is just a grayscale value between 0 and 255. 255, as you can see here. All right. So that's sort of the way we can do that. So plt.imshow actually gives us the image. Now we can also print the y values. So if you do print y train 1, we should get the corresponding y value to this x just be 0, right? 0. All right. So now we've sort of visualized the data in a way. So now let's actually flatten the image for the neural net. So what exactly do we mean by flattening the image? So when I refer to flattening the image, that's sort of just taking this 28 by 28 pixel image and putting it into a vector. And what I mean by a vector is just think of it just as an array with 28 by 28 elements in it. All right. So that's essentially what we want to do when we're flattening the image. So we're flattening the image into a vector, one-dimensional vector. All right. So one-dimensional vector. And in order to do that, first let's define this variable called the number of pixels. So the number of pixels is just the number of pixels. So in this case, we just multiply. We just multiply 28 here by 28 to actually find the number of pixels, number 1 by 1 pixels. All right. So the way we do that is we take number of pixels equals xtrain.shape1, which just takes this attribute here. I recall that in programming, this is 0 and this is 1. So we take our 1th element. And then we multiply by xtrain.shape2, which is this 28. And then when we do 28 by 28, we get actually the number of pixels. So the number of pixels is 784. All right. So now let's actually do the actual flattening. And this is sort of the way we'll actually do the flattening here using this piece of code. So now we've sort of flattened the xtrain and x test vector. I guess in order to look at it, let's do xtrain.shape. We'll see that this is now a 60,000 by 784 dimensional vector. And if we do the same thing for x test, we see that x test is 10,000 images and each is a 784 dimensional vector. All right. Now we go into something called normalization or feature scaling of data. And what do we mean by this? And so essentially what this is recall that our grayscale image here, each of the 784 of these 1 by 1 pixels, each of the values corresponded to some value between 0 and 255. However, and I won't go into big detail as to why this is, why we want to do feature scaling, but just for now, just think of feature scaling as a way to make the neural network perform better. All right, so essentially we feature scale data from 0 to 255 to a number between 0 and 1. And the way we do that is we just take X train and we divide it by 255. We take X test and we divide it by 255, thus transforming the array into a number between 0 and 1. And by the way, we'll be talking about this in the next lecture where we discuss normalization in greater detail. So we'll spend around half the class next time actually discussing normalization and feature scaling techniques in greater detail. So let's run this. All right, so now if you sort of look at our data set and we sort of run this again, we'll see that we no longer have, it's no longer a number between 0 and 255. Instead, it's sort of a number between, it's just a number between 0 and 1. And the reason you see so many zeros here, as you can see here, are just because a lot of the space is just white space, and they just correspond to a grayscale value of 0. So now we have sort of normalized the data. Well, one last thing we have to do is to actually use the two categorical method, the two categorical function here. So as you can recall that we imported this two categorical package. And essentially what that does is now instead of having instead of having one output node, you'll have 10 output nodes corresponding sort of like as the probabilities of being each of the nodes. So what exactly I mean by that is instead of having one node, we'll have 10 nodes which correspond to numbers 0, 1, 2, 3, 4, all the way up until 9. And each of the nodes, and essentially we want to pick the number, we want to pick the node which has the highest probability of being that. Okay, so that's what we mean by using the two categorical. And now another thing we want to do is a number of classes. So a number of classes is just sort of the number. So since this is a classification problem, we just want to determine the number of actual total classes. So in this case, the classes are just numbers between 0 and 9, and that means we have 10 numbers, and the 10 numbers is 0 to 9. So you have number of classes equals ytest.shape1. And if we actually do that, we'll get the number of classes. Let's run that. All right. So now we actually create the model. And first what I'm going to do is just create a sort of template model called classification model. And then I'll fit it for our particular data. Okay. So first we have, let's create this classification model. And we first define this model or initialize this model to be a sequential model. All right. So this sequential model is loosely essentially just sort of initializing it as a neural net. So now let's first add our first layer. And this is important. So we're using the ReLU activation function. So I think Dr. Willard mentioned it in his lectures. So ReLU is a very popular activation function, and we'll be using this in this neural net. So first, our first layer is just going to be a layer with just 784 nodes. So 784 is the number of pixels. So 784 the input nodes, and each of those just correspond to the number of we just input each of the pixels as inputs to our layer neural net actually. All right, so this is our first input. Next we create a hidden layer, and the hidden layer is essentially create a hidden layer, and the hidden layer will define it to have 100 just to have 100 nodes. But we could have changed it to 75, 125. This is just a typical example. 100 is a pretty good number that I put. Okay. So after we create this hidden layer, we have our final layer, and in the final layer, we actually have 10. We'll have 10 nodes corresponding to numbers between 0 and 9. 0 and 9 as our output nodes. Okay, and we'll be using the softmax activation function. And softmax is a very popular activation function used in the final node. All right, so now we've sort of created our neural net. And now let's actually train let's start training the neural net. So we're using the model.compile. So first, before we actually train a neural net, we could tell the model what cost function or what loss function we want to use, what optimization algorithm we want to use, and what metric we want to use to determine how good the model is doing. Okay. So So I'll be using the categorical cross entropy loss function, and this is loosely analogous to the cost function of logistic regression. All right. So and you have to be expert in the actual cost function. Just know that this is a function that sort of that pretty effectively measures how bad the model is doing. Okay. And now we'll be using this optimizer. Now we'll be actually minimizing this cost function. And in our previous lectures, we learned gradient descent to actually minimize this cost function. However, while you could use gradient descent, in this case, we'll be using another algorithm called sort of the Adam optimization algorithm. We'll be using Adam to actually minimize this. Categorical cross entropy and find the optimal parameters. Okay. So let's do that. And now we have sort of initialized the model. And now we're almost there to actually build the model. Okay. So now we'll have our model to be our classification model, to be instance of our classification model. And then we will fit the model to, now we'll fit our model to our X train and Y train to actually train the data, to actually train the model, and have X test and Y test to actually see how good the model is doing. So we're going to be using these two things to train the model and these two to test the model. And we will run this with 5 epochs, meaning that we'll just run it for 5 iterations. So we'll essentially train this model 5 times. So that's what epoch means. Okay, and now we'll have our scores to be the model evaluate X test and Y test. So that just evaluates how well the model is doing. So let's run this. And now let's wait. So as I said before, I have 5 epochs. And now we're training the model to actually find the optimal parameters, okay? And the amount of time it takes to train is highly dependent on 2 things. So one is your implementation, and number 2 is sort of just how fast your computer is. So in this case, I'm using the implementation straight from Keras, so this is pretty fast in that sense. However, my computer might not be the fastest. Other computers might be faster, and we can do it faster in that sense. Okay. So now let's just wait for the model to finish training. Okay.
Your computer's running out of battery.
Oh really? Okay. Okay. All right. Yeah. So let's just wait for our model to run. It shouldn't take very long, but let's just wait for some time. In the meantime, let me actually charge my computer. Yeah, so one thing you can probably observe here is the following. So we first see that our accuracy is generally going up with each epoch. So you can see that we have accuracy 0.9428, and we have 0.9763, and it's going up and up, okay? So going up and up, and that corresponds to a lower and lower loss. However, note that more epochs isn't necessarily better. So as Dr. Willard said, so yeah, we actually see an example of that. So as Dr. Willard said, a neural net can overfit or underfit. All right. So underfitting situations occur usually when we don't train the model enough. So we only train maybe for 1 or 2 epochs in this case. However, if we train it for like 50 epochs or something, then the model will overfit. So it'll start memorizing the test data, then the train data, okay? And thus will perform worse on new test data. And if that's confusing, that's completely fine. We'll be discussing this again in the next lecture, all right? So we actually kind of sort of experienced overfitting here. As you can see, we had pretty good accuracy here, and then it went down to 0.967, okay? So our accuracy went down, and that's one reason for this might be overfitting. So now let's actually find the accuracy of the model. So let's run this to see the accuracy. So now we'll see that the accuracy is 0.97, pretty good, and error is 0.023, and this accuracy is really, really good in my opinion. Okay, it's quite good for this task. So it's accurate approximately 97% of the time. Okay. So now you're sort of done. But now one thing you might note is how, so there's just two questions you might be asking. One is just how well is my model doing? So two questions. So one question might be for the correct one. So which test cases is my model doing well in, and in which test cases is my model not doing well in? So we'll thus investigate both of that. So first, let's see which test cases our model is indeed doing good at, and it turns out that we're doing good 97% of the time. So first, let's go to our first example. So we have predictions 0 and x test 0. Okay, so that's our first training example. And we see that, as recalled, our first training example was 7, and it turns out that our predictor indeed said that it was 7. Okay, so we were correct there. Now let's do predictions 2 and x test 2. Let's run that. We'll see that that has 1, so the actual image here was 1, and the prediction was 1 as well. So let's do this for here. Let's do x test 3 and predictions. And do predictions 3. Let's run that. So we'll see that 0 and 0. Okay. So even more importantly, it might be in which cases is the neural net performing bad. So if you actually learn that, we could most likely improve our neural net that way. So let's actually look at that. So first, let's create this array, this results array, and essentially what this results array does is let me just print results. It essentially checks when it essentially outputs true when it performed correctly, and it outputs false when it performed incorrectly. Okay, and now we do np.argmax y test, and that thing this essentially just outputs what the actual y value is for each of our testing example. So now let's actually create this array called wrong predictions using our results array. And essentially wrong predictions, if you print our wrong predictions, it essentially just outputs indices of when we had wrong predictions. Okay. We see that we got wrong 18, 65, 104, so on and so forth. And actually we had 10,000 examples, and it was surprising how few times we were inaccurate. Okay. So now let's look at the ones we were inaccurate on. So first, let's look at our first inaccurate one. Okay, let's run this. I've already run this before, and that's why we already have this going on before. So first, let's run this. Sorry, let's run this first. It says ypred is not defined. Here, let's change it. I think I see what it is. So I'm not sure why ypred's here, but it should be predictions. Yeah. So now what we see here is that, so this is our first wrong example. So what you can see is that, so here the image was a 3. I think this is a pretty obvious image. It's 3 here, although it might be a bit blurry. Our neural net said that this was a 5, even though in actuality it was a 3. So it's sort of blurry, as you can see here. And I think the key point that I want all of you guys to take out of this is that the ones where the neural net doesn't do well, it's not just a random example. Instead, it's just something that's actually hard to classify. Either it might be really blurry, or just the way of them writing might be non-standard. Okay. So now if we look at this here. So let me just change all my ypreds to predictions. Not sure why that happened, but okay, predictions. So we'll have this. Okay, so as you can see, this 4 is pretty blurry. And the actual class is 4, but the neural net said it was 9. And as you can see, I guess one similarity between most of these is that all the ones where it predicted wrong, it might be very blurry, because at least this 4 is a pretty standard way of writing a 4, but it's quite blurry, so the neural net got confused. So now we have this. This actual class was 9. The neural net thought was a 5. Okay. And again, here in this case, as you can see, the 9 isn't completely closed. And again, it's very blurry. So this is actually a very interesting example. So here, so this is a 2, okay? And in this, even though the actual class is 2, the predicted class here was 1. Okay. And the predicted class here was actually 1. So that's interesting. And this was actually, and the reason this is bad is that this is a non-standard way of writing 2. And finally, let's look at our last. This is not our last wrong prediction, but this is one of the last wrong predictions. We see that here we actually outputted 3, and the actual class was 3, but the predicted class was a 7. And that's about it for this programming demo. And hope you guys enjoyed it. We now be posting this code, and we'll also be posting a recording on the Google Classroom. All right. So the Google Classroom. So if you want, we can run this over again. You can maybe change some stuff, maybe add more layers or whatnot. Okay. So now on to questions. So I see that we have a lot of questions here. So 24 questions I see.
Trace, I've been trying to do a pretty good job keeping up with these, so we might open it up for new questions, but I do see one here at the end that we might be able to answer about the incorrect predictions.
Oh, that's a good question. What % confidence did the answer get predicted with? Here, I'm actually not sure about that. Here.
We could probably try. Let's take one of the indices for one of the incorrectly predicted ones and look at predictions for that value.
Okay. See 18, for example. We could maybe do argmax. Okay. Here, wait, what exactly do you mean?
Let's just do, instead of argmax, write predictions there.
Predictions?
Yep. But you'll need to change the parentheses to square brackets.
Oh, oh yeah, exactly. Yeah, here. Yeah, so here, as you can see here, this just corresponds to like the probability of giving each of these. So wait, which one did it correspond to here? So the predicted class was 5. Yeah, so this was the probability, I guess 0.1. Wait, yeah. Or actually this one.
So no, that's actually, you're looking at I equals 0 below that, not I equals 1.
Okay, never mind.
So it looks like it actually predicted 9.
Yeah, it's highest accuracy.
But it also thought that it was possible that it was a 4. So if we look down at that, yeah, so it predicted 9, but it actually was almost just as confident that it was a 4. So the 9 was just a little bit higher in terms of the probability associated with it.
Yeah, actually, yeah.
I would say that it wasn't super confident in its prediction.
Yeah, but I'm also curious what exactly it said here. So I equals 3. I can look at I equals 3 here.
So Rick just asked the question, where do we see the confidence? So what we're doing is we're looking at the predicted probability for each class for the observation in question. So for that first one we were looking at, I equals 1, we were looking at the different probabilities associated with each of the observations. And the probability was highest for the class 4 and the class 9. And then there was a little bit of chance that it was class 5. Here, if we look at this output that Shreyas has generated, it looks like it's actually very, very confident that it's a 9. It looks like it's about, says there's a 97.8% confidence that it was a 9. But what was the actual?
Oh, I believe it was a 2.
Yeah, so it was actually very, very confusing. Or the neural network was very confused. In response to Douglas here, we actually did use the softmax layer, which is what transformed this from into the probability space that we see here. Oh, was it a 1 that was predicted?
Oh, really? Yeah, I think, yeah, I probably looked at the wrong one. But yeah, I think we were looking at this one. That's why.
Okay.
Wait.
So in general, when you're looking at this, it's probably better to print the confidence alongside the predicted class and the actual class when you're looking at the image directly. But that was an interesting question, so I appreciate Shreyas trying to do this kind of on the fly here.
A great question, yeah. So any more questions? And then 9's confidence was much higher.
That might have been for the previous prediction.
Yeah.
So we've gone a little bit over tonight, but do we have any more questions? Yeah, I don't know. That's a very interesting question, Noah. I don't know that it's really possible for us to know where the drawing started and ended. So I know a little bit about this data set, and it was actually taken from, I believe, middle school students who had to enter numbers on a standardized test, and they scanned all of these in. So we don't really know how the numbers were drawn. We just have the kind of resulting output, so we can't trace actually like the order in which different features were drawn, but that is an interesting question. And if you were able to observe the person writing it, that's probably another input you could use to be more confident about your predictions. Do we have any more questions this evening? It's a good question, Rick. So if the orientation was different, so if we had rotated one of these by 90 degrees or flipped it, it would probably confuse the model in this case. There are more sophisticated ways to deal with that in other types of images.
Yep.
And so, for example, if we were looking at images of faces, we wouldn't want it to get confused, for example, if a face was mirrored. But here, since these numbers have a correct orientation, we wouldn't want to kind of delve too deep into trying to identify images that were drawn incorrectly. And yes, Rishi, you're correct. If they were all sideways, it wouldn't make a difference. If we rotated every image by 90 degrees, it would still learn to be able to classify them directly. It's just looking to make sure that every example that it sees follows kind of the same pattern. Sorry to have interrupted you, Shreyas.
Oh, no problem. That's completely fine. So what I was saying is that actually rotating the image in for example, facial recognition, that's a great way to generate new data examples. Yeah, so that's called, I think it's called artificial data. So that's actually a really good way to get more data in that sense. See. Yeah, so Amy, so essentially what you would do is you would just add to model.add and just add another layer that way.
Sure, as you could probably show that real quickly.
Yep. So let me go back. Yeah. So for example, let's just copy this again. Here, okay. Run this. And when we actually run this again, we'll get a different result here. So adding more layers doesn't always make this model perfect. Doesn't make this model better, because you can start overfitting this scenario if you add too many layers. But 2 shouldn't be very much at all.
You'll also see that it will take a little bit more time to run, because essentially what we've done is we've added another 10,000 parameters that the model needs to learn. So it looks like it's comparable in terms of speed. That might be because Shreyas's laptop is plugged in now, and it can operate it at full capacity.
Yeah, so the speed actually like heavily depends on the machine. For example, when I was using our brother's machine, each epoch took like a minute.
And on my desktop with a GPU, each epoch took about 4 or 5 seconds. So it is very dependent on your computing hardware.
I forgot what. Yeah, it would. So yeah, so Rick, it would indeed affect, so sort of how blurry it is would affect the accuracy of the neural net. So as you could see, many of the ones like where it's classified incorrectly, for example, this three was due to it being very blurry. So it would impact the accuracy to some extent. I think someone else asked a question. Would it be possible?
So Rishi asked a question, with the binary classification, what would the activation function be? That was the binary cross entropy function. So if you were to go back to our logistic regression lecture, that's where we described that function. And graphically, basically, the function is small if you have a low confidence prediction, and it gets very, very big if you have a high confidence prediction that you get wrong, and it's about 0 if you have a high confidence prediction that you get correct. So you were okay. Yes, I misread. You're talking about activation functions, not cost functions. My bad. For the binary classification, you can use the same activation functions. You could use ReLU, you could use hyperbolic tangent. We could actually use different activation functions for each layer. If Shreyas wanted to change one of those ReLUs to a hyperbolic tangent, he could go ahead and do that. And I'm assuming it probably wouldn't impact the accuracy that much.
The rarity change is sigmoid, I believe.
Yeah, I mean, I don't know if you need to do this right now because I think we're way over time, but
yeah, it's fine. Yeah.
People can play around with this and try out different activation functions if they're interested.
I believe that was the ReLU, but I'm not too sure.
So the activation function, that was, I don't know that has a specific name. In math, it's called the Heaviside function. Basically, it is a step function, which is -1 when the input is negative, and 1 when the input is 0 or positive. I wouldn't necessarily use that all the time. Right, there is a jump discontinuity. So I would generally, when training a neural network, in terms of activation functions, use something that's differentiable, like the sigmoid, which kind of mimics that same function, but without the discontinuity. Well, Shreyas, thank you for an excellent demo. If there's any more questions, I encourage people to join in and post something on the Google Classroom, and we'll be happy to answer it later. We'll go ahead and post this Python notebook and the lecture slides as well.
All right. Bye, everyone.
Thank you, Shreyas.
Thank you, Jeff. Bye.